Friends, welcome to this series of tutorials on network analysis made simple. In this tutorial, we shall discuss on series resonance circuits. Friends, first let us understand what a resonance is in general. Then, what is resonance in electrical circuits and when resonance is observed. Then, let us derive the equation for the series resonance frequency and discuss regarding the frequency response of series resonance circuit. Finally, let us summarize by listing the characteristics of a series resonance circuit. Friends, resonance is associated with energy in physical systems. In general, phenomenon that happens so often in practice and in so many systems, but sometimes we ignore its existence. In most general terms, resonance is a representation of energy exchange from one form into another at certain frequency. Bridges and buildings resonate when excited by external force. Circuits resonate when electrostatic energy stored in capacitance and electromagnetic energy stored in inductance is exchanged. Lasers are resonant cavities where photons and electrons exchange energies at a predetermined frequency. Any musical instrument resonates at frequencies defined by the thickness, length, and the tightness of the string. Next, we shall see when resonance is observed in electrical networks. Friends, when coil and capacitance are connected either in series or in parallel across an alternating supply of varying frequency, resonance phenomenon is observed. Resonance phenomenon is a specific condition of the circuit when maximum energy is released or the energy is exchanged by the circuit elements. In fact, the resonance condition can be achieved either by keeping the network elements same and varying frequency or by keeping the frequency same and varying the frequency dependent circuit elements. You know that inductance and capacitance are the frequency dependent circuit elements. In the circuit shown, the coil is shown as an inductance of L henries in series with the resistance of R ohms. It is true that every coil of N turns has some amount of resistance, however small it may be. Similarly, the capacitance also may have small amount of resistance. But both resistance of the coil and the capacitance are assumed to be added in the resistance of R ohms in the circuit shown. Thus, the inductance of L henries and the capacitance of C farads are ideal circuit elements. But what is the condition for resonance? We know that the inductive reactance XL is equal to 2 pi of L and that is equal to omega L ohm. And the capacitive reactance XC is equal to 1 upon 2 pi of C and that is equal to 1 upon omega C ohm, where omega is equal to 2 pi of radians per second. We know that in phasor form, the inductive reactance XL is equal to JXL ohm and the capacitive reactance XC is equal to minus JXC ohm. The excitation applied is an alternating voltage of varying frequency as shown in figure. The response is I, the current which is dependent on the impedance, where impedance Z is equal to R plus J XL minus XC. Here we assume that XL is greater than XC. We know that as frequency of increases, XL increases and XC decreases. In other words, by varying the frequency, it is possible to reach a point where XL is equal to XC, in which case Z is equal to R and the current in the circuit will be in phase with the voltage applied across it. Therefore, this condition is said to be a point of resonance. Hence, the series resonance circuit is said to be at resonance when inductive reactance XL of the circuit becomes equal to the capacitive reactance XC. The frequency at which the resonance occurs is called as resonance frequency and is denoted by F naught in Hertz or omega naught in radians per second. We know that at resonance XL is equal to XC. Let omega naught be the resonant frequency in radians per second. By substituting for XL and XC, we get omega naught L is equal to 1 upon omega naught C and omega naught squared is equal to 1 divided by LC. This can be written as omega naught is equal to 1 divided by root LC or F naught is equal to 1 divided by 2 pi root LC. Now, we shall study the frequency response of a series resonance circuit. We know that at resonance XL is equal to XC and omega naught is the resonant frequency in radians per second. Let I naught be the current at resonance, but in general I is equal to V divided by Z. Assuming XL greater than XC, we get I is equal to V divided by R plus JXL minus JXC. Since XL is equal to XC, at resonance we get I naught is equal to V divided by R. The frequency response of a series resonance circuit is the variation of response which is current I with respect to frequency. The frequency response curve is shown in figure. We see that at off resonance frequencies on both sides of the resonance frequency of naught, current decreases because as F increases beyond F naught, XL increases, and if F decreases below F naught, XC increases. Finally, let us summarize by listing the characteristics of the series resonance circuit. The first, at resonance, XL is equal to XC. Next, impedance will be purely resistive and hence Z is equal to R. Further, current will be in phase with the applied voltage and is maximum at resonance and I is equal to V divided by R at resonance. Power factor of a series resonant circuit is unity at resonance. So, at off resonance frequencies, when F is greater than F naught, the inductive reactance is more dominating than the capacitive reactance, and hence the total impedance will be inductive. Similarly, when F is less than F naught, the capacitive reactance is more dominating than the inductive reactance, and hence the total impedance will be capacitive. Friends, to appreciate the concepts that are explained in this tutorial, I suggest you see the video of 1 hour only on resonance and sound of music by Professor Walter Levin. You can reach that video via link indicated. He has demonstrated the effect of resonance beautifully with examples. Hope my presentation has kindled some of your thoughts. Please forward your feedback and suggestions to my email. Thank you for watching.